Hey everyone, we are Astra, and our project was about creating a tool that minimizes the energy used in agent-to-agent communication for solving complex tasks. And so, in the demo that you see today, we provide a use case scenario of AI agents exploring a space, like exploring a space such as, Mars, and communicating to achieve a goal of identifying water, and you'll see how that performs. Very selfless. What's-
Yeah. Yeah, I can talk a little bit about the back end. So what we did was we made two rovers. They're like filled with a little fake information right now, but they would be like in theory they would be actual information that the rovers on Mars would collect, and it would be in two sort of sets. So rover one hypothetically has all the solutions and has an empty dictionary filled with like observations that rover one would or rover two, sorry, would then put into rover one and report back. And then rover two, if they come across any problems, they say, hey, rover one, I have a problem. And then rover two or rover one gives the key problem, returns it back to rover one or rover two. It's a little confusing between rover one and rover two, but basically, rover one has all the solutions so that rover two doesn't have to carry that much information with it. And it can also just constantly update with a human in contact with rover one. Yeah.
So for these rovers to interact, we implemented two agents using GPT API, and they're pretty much having a conversation with each other. So if rover two comes across a problem, it'll ask rover one like the potential solution for that problem. So that was our agentic interaction. And in the demo, we have like a parent, and then we have a bunch of children rovers. So the goal is to uh, go on the surface of Mars and try and find water. And the other thing that we implemented was tokens, because we wanted to see how little tokens can we use to convey a decent amount of information, and that's like based on like bandwidth, because there might not be as much bandwidth, so you want to reduce the token size. So less tokens means less information, but how efficient can that information be? So that's another thing that we tested as well.
Okay, demo time. Okay, so to show this, you need to see two teams, right? So one team competing under different conditions than the other team. And the key thing what we did is we enabled new way of agent-to-agent communication. Why? Because yeah, we're communicating under very low energy, very low bandwidth, and difficulty trying to reach each other. So we came up with that the key problem that we have and rovers in space is how much tokens they can be exchanging. So we actually came up with a few ways of compressing the token output from one agent to the other. So we used contextual expression that Sophie talked about. We're using some semantic compression by using the neural network itself. So in this case, OpenAI is the network that is embedding the compression, yeah, on the output that it's generating. And the last thing, we're doing some fingerprinting, basically some hashing on the tokens that are sent out to the other model. And because the models are exactly the same, we're leveraging their the same representation of concepts that they know about. So now, how does it look like? So we'll give blue team a compression here in this case. We'll turn up the tokens for both, just to speed it up a little bit. Set the maximum token limits, just let's say to 4,000. Let's launch this mission. Now, what is happening? So we have, in this case, 3 red agents, OpenAI in this case, 3 blue agents, and they're looking for the water. That's the light blue dots. Well, we see what's happening down here, and we see that the agents are communicating about what you're going to do. So one moves north, west, and east. And then blue is using a very different way of communicating. So it's basically sending S72-15.45. Now, it comes down to pretty much a similar way of coordinating, but why it helps is that you see the compression. It actually is saving about 90%, so an order of magnitude in its tokens that it's using in the coordination. And that's what we're going for, because coordinating is pretty energy intensive. And you see the tokens that they're racking up. So red team is already at 1,100 tokens in this game. Blue is still below 100, now passing 100. They're a little bit lucky that they already found 2 sources of the water. Yeah, so what this is just showcasing as a demo is that agents, if you let them communicate, let's say in small groups, they rack up tokens very quickly. On the first one, we made a mistake. I made a mistake, and it reached 80,000 tokens in not even 2 minutes. So, and there was no like kill switch or stop button. So this is important. If you have, let's say, groups or swarms of agents cooperating, you want some way of really efficient communication between those. So yeah, we're managing here more than an order of magnitude. Blue team is ahead. I think, yeah, this game will go on for a little bit longer until blue finds all or they run out of tokens. Yeah, but that's it. So it showcases ASTRA, which stands for, of course, agent to agent, meaningful token minimization exchange in extreme conditions, under extreme conditions like space. Does it make sense? Yeah.
Okay, about future plans. As you could check, this is a new even research topic. I'm serious. Really, like, if we are serious about like using LLMs in space, this is a serious matter also because as you probably may know, the energy consumption of even the inference of these models, it can be really costly. So yeah, the next level, I mean, the next features that these simulations should have is like really realistic setup, like from the energy point of view. This is one of the, let's say, most limiting factors in space. So you have a certain amount of energy, you have a certain roles. You have, for example, 3 roles. So one role is just the explorer, the other role will be the driller, and the other role will be the transporting machine. So you have these 3 roles. Both, like all these 3 roles have like limited energy for all the actions. So you can, let's say, move or you can communicate, and the communication also costs energy. So in that environment, do a realistic, let's say, simulation of this compression protocol, which is very, I mean, if you think about it, it's not like, doing WinZip. We are using the structure of the model itself. So with no prior knowledge, one model can communicate with each other and understand what they are talking about with less token. I mean, this is very interesting. Thank you.
How did you choose the compression for the token?
He started.
So we first did some semantic compression, and then the idea was, well, we don't need a separate model to do semantic compression like a semantic model. We can actually use the model itself to do the compression. Then we did some sort of contextual fingerprinting. So based on different states, we pre-programmed, like if you're sending this message, it has this meaning. And so you can also, you already worked out like that they can create their own blueprints and encode it into one token, basically. So they can share this new way of very efficiently representing a new situation. Hashing is going on. And if you put that all together, you get very cryptical messages that we can no longer read, but you can also decode it in the same way, of course. So that's happening under this. So we see they're just sending like messages like this. Yeah. Yeah. So semantic fingerprinting. I think that's a nice way of putting it.
Okay, yeah, cool.
Any other questions?
It's how much prompting is involved. Like, do these have like massive system prompts beforehand to like lay out the compression stuff that you guys are doing, or is it like relatively terse?
No, very, very limited. Actually, we started by just putting in the objective in the top, but then we had to redo that. There's just a simple objective: find the water, and then the only thing that they can do is communicate with each other sequentially. So they each get a turn, and then they communicate to their team members, and then they get the next team member gets a turn. And there's no other system prompts except the token limit that they have to adhere to.
Okay.
Yeah, and that's it. So it's very limited. Yeah.
What a lovely demo, by the way. It's so cool. I love it. Super cool visual. But yeah, which layer was the most brought the most performance efficiency? Was it the hashing? Was it the one token blueprint type of thing to speak their own language, or was it the one rover out to many other rovers?
I don't know. I think we implemented
All at once.
yeah, multiple things at once.
Okay, and then when they like communicate with each other, it's like, does the decrypting and encrypting, is that like take extra energy when they're decrypting and running that, or is that super efficient?
I think that for decrypting or encrypting, that definitely take extra energy because you need to do a lot of computation, which consumes a lot of energy on that. But it's like, but compared to while you are traveling, that's still gonna to be minimized. It's not like you are going to train a AI model using a lot of GPU spaces, but that one can be almost minimized.
No, but I think it's also a matter of research. I'm not sure 100% what's it. I mean, it's true for, let's say, encryption in general as a concept, but I'm not sure if, doing the thing that we are doing, it will, how it will work.
Yeah, what's one token versus encryption, decryption for energy?
Not really. It's a whole research topic. No, it's serious.
Very cool demo. I love it. You guys thought about it very differently than I would have. I would have thought of it as just a byte stream, and traditional compression would have been like my go-to. I'm curious, did you guys compare that, or? Yeah.
It's a very good point also. Yeah, to have that baseline. Yeah.
And also in our case, I think we are, instead of using like human understandable language, we are also ask AI to build their own language, try to do the encryption and the decryption. Basically, it can take like some into the next level of encryption knowledge, which we were never used to do before.
Right. You're just kind of getting into information theory, and like I'm curious how much you can encode versus like an ideal compression is very close to entropy. So, yeah.
Yes, we talked about it. We talked about bioinformatics and the tree. But then we thought, well, actually we have a full representation of all the knowledge that has been going into this model. And let's try to leverage the neural network, because the other rover or the other space part has the same model and is carrying that same model. So why would we?
Yeah, maybe that does get you
change. Yeah.
beyond the limits. Maybe the limit for traditional compression. It doesn't presuppose having this large corpus of knowledge. I don't know. It's very interesting. Yeah. Yeah. Cool
No, I
project.
mean, this comparison should be in the paper as well.
Yeah. Yeah.
And just do they have a strategy to find the water? Because I feel they haven't found the 3 water already.
No, blue. Yeah, they're still
They're still looking. Do they have a strategy or?
Well, I think what happened here is that, yeah.
Okay, that was a bit concerned. But also, do they have a strategy or?
I don't know if it's code like if a particular strategy is coded into how they move, but we did have a conversation about what kind of algorithms would be used for exploration, and that's this is just one task. Exploration, it could be applied to many different features of large language model teaming. So I think the algorithm would change, but I think these efforts were more what happens when we just give it a prompt and tell it to go.
We're really literally seeing OpenAI 4.0
Trying
to just communicate through a text prompt, so many tokens max, and then the others are responding with a new move, and then it's like the basics.
Yeah, cool.
I mean, this is the gentle way, like to find an algorithm. The brute force way would be, hey, this is your energy that you have to accomplish this task. If you get run out of your energy, you are fucked up, and you need to figure it out what's best, and try the models in that situation. How do they perform? It would be interesting to see.
Maybe you guys mentioned this, but is there a particular problem with game theory that you got inspired with? Why exactly this setting? Is there something that's already studied, the same type of game?
No, we didn't go into game theory or really delineate it nicely, like this is a fully observable game, with sequential moves and do that whole state space, but we basically started from the situation, so how can we get agents to cooperate with the least possible amount of tokens? That's what we came to, that's our essence actually, that's the core. And all of this is just the space case we've been now using to show what happens. But I think, so the heart of the exploration today was limiting the amount of token usage and agent cooperation to the bare minimum and see what happens. And Blue still won the game, even though they had so I think
should definitely make a blog post or at least workshop paper.
Yes.
We should near reach deadline in 1 month.
So Sundai papers.
No, really, you guys. There's so much interesting questions.
But it's this exploding amount of tokens, right? When you have a lot of agents that start to communicate, it's this exponential curve that we're getting on. And if we're not trying to get the other exponential down, it's going to become too large for agents to effectively communicate together. So, I think this is.
So next week is going to be growth. So workshop with New Reefs is only 2 pages of yeah. You can do it in a day. That's something that 100%.
What happened to the frolic?
You vibe code LaTeX. That's how you do it.
Okay, so thank you.
Thank you.